Hi, how are you guys today?
Hello.
Good. Fantastic.
Good. You guys are 5619, right?
Yeah. Yep.
And do you have your engineering notebook?
Yeah, here.
Okay, awesome. Thank you very much. Okay, whenever you're ready.
Hi, I'm Zach. I'm new here.
Continue.
Oh, I'm Max.
I'm Wanwan, I'm a sophomore.
Hi, I'm Sarah. I'm a junior.
I'm Ellie, I'm a sophomore.
I'm Aiden, I'm a sophomore.
And we are 5619 Robo Cardinals. So today we're going to talk about how we designed modular parts and then combined them into a cohesive robot. But before that, I want to talk a little bit about game strategy. So when we looked at the game, we noticed there were two big point moves, autonomous and lifting. That being the case, we really pushed in those two fields. However, we also considered other strategies.
So one of our options when initially deciding what we were going to do with our robot is we decided that it would maybe would be more scoring effective in terms of blocks if we could instead launch the blocks instead of simply placing them. So we had two main original mechanisms. Now the first one was more of a catapult, slingshot, crossbow type design where we would launch the blocks through a mechanism that would simply fling them, and that turned out to be very reliable, however not very efficient in terms of the mechanism required to actually make that work. Now, our second mechanism was simply two spinning wheels, which blocks would be pushed through. This mechanism turned out to be a lot simpler to build, however its reliability in terms of scoring was far too much work to actually make effective. So we decided to go against that, and instead we explored other options.
One of our main ideas in our robot is our lifting. So one of our main ideas is that one of the ways that we thought we could lift the robot was that we had two motors and two servos, and the motors powered the servos with string on it, and there was a bar, and it lifted up the robot, and the robot went up.
So the next thing we had to do was find a way to get the string onto the bar. So we designed this three-jointed arm to lift the string and put it on the bar. And with this arm, we used servos. It was a three-jointed arm because we needed something that was tall enough because the bar is 33 inches off the ground. So we used servos initially to lift the arm, but we ran into some problems regarding the servos.
So in order to lift the arm up, we needed to control the servos in varying degrees. So imagine you're driving in traffic, you need to pass another car to your right. You need to vary your speed based on where that car is until you're in front of that car. In the same way, we had to continuously vary, in a very dynamic way, the servo values. And we found that three-jointed arm couldn't be modeled using linear algebra. So instead, we decided to seek another option.
So we decided to go with a two-jointed arm, and instead of using servos, we'd use springs because there was already energy in there, so we wouldn't have to power up and all that stuff. Unfortunately, the large string for the main arm connecting to the robot was not strong enough and wore out too much, so we just had to replace it with surgical tubing.
And Holden will talk here.
Yeah.
We got Holden.
And then I will talk after Holden. So one of the key aspects of our robot is the fact that we used the 3D printing to create a lot of the specified parts we needed. The reason we decided to go with 3D printing is we needed very specific parts to serve certain functions, and the best way to do this was to design them in a CAD program and print them. This allowed us to make more specified pieces for whatever we needed to achieve. One example of this is the main component of our robot, which is the spools that actually lower the arm which raise the robot. Now this, the spool design actually went through multiple iterations before it became the spools that they are now, and it required a lot of work and a lot of teamwork to design an effective spool.
So another area of inquiry that we pursued was the autonomous section. We decided the best way to score the most autonomous points was to have a simple arm, such as that swings from the robot to the place where the IR is, scores the points there, and then drives over to the ramp to get the maximum number of points. And how we designed the IR system for that is we made a simple check. If the robot was in a certain place in space and if the IR reached a certain limit, then the block would be deposited. And we thought this would work perfectly. However, in the first competition, everything was right with our code and our engineering. However, the IR sensor itself, the game officials did not set it the right way, and so it failed, which we were a little disappointed about. However, in the second competition, we made sure the IR settings were correct, and our autonomous worked 100% of the time the way we wanted it to.
Now all these modular sort of pieces have to come together in some sort of way, so we decided to use a very basic chassis so we could kind of tack on different pieces whenever need be. Although this chassis is very basic, it can also go very fast because we have a 2-to-1 gear ratio. And during the first and second rounds of robotic tournaments, we found that the wheels had less traction than we thought they would. So we replaced the back wheels with more traction-y wheels that didn't allow us to turn as much, but had traction. Flat.
Flag.
Flag. So our lifting was great, and our autonomous was great. But we found a problem in Endgame. In the second competition, in the first competition, we were paired with teams that could hang just as well as we could. So we decided to build the flag so we could go for that 35 flag points while our teammate was going for the hang. So far, it remains to be tested. We'll see how it goes at the competition. Is that what we're done?
I think that's it, right?
And
Any
that's it.
questions?
Oh, no, wait, no. Oh, wait.
And now,
There goes there. Oh.
So, we combined all these modular pieces we've talked about into a cohesive robot. Voila.
What are you doing?
Here are the spools that we 3D printed and designed that pull the arm down once the arm is positioned over the bar. Here's the arm mechanism, which releases with the string being let out and allows us to hang. Here is that famous autonomous arm, which allowed us to score for the IR every single time in the second competition. And lastly, this is our flag mechanism, which allows us to score that 35 points when our opponent is going for the 50. Thank you.
Good.
We are 28